All right, welcome everyone. Today we're going to be starting our new unit of material, and that's polar coordinates. So in today's lesson specifically, we're going to see how to plot points in this polar coordinate system. And then next time we'll see how to actually convert back and forth between Cartesian and polar coordinates. So today we're just going to introduce the polar coordinate system and see how to plot points. All right. So first of all, what is a coordinate system? Well, it's a way to describe a point in the plane using an ordered pair of numbers. So probably what we're most comfortable with is the Cartesian coordinate system. So this is the normal x and y axes that we draw. So normally when we talk about the plane, we kind of pick a point, which is the origin, and then at that point we draw in our y-axis, which is vertical, and then our x-axis, which is horizontal. So our origin is right here, and then we have our kind of our two coordinate axes, the x and y axis, that go off in that are perpendicular to each other. They're at right angles to each other. And they intersect at the origin. Now, if we were to select a point at random, point P here, normally the way we describe point P is with two coordinates, so an ordered pair of numbers, and normally the x coordinate comes first, the y coordinate comes second. And so what the x value here really represents is it represents the horizontal directed distance this point is away from the origin. So it's the horizontal distance. And it's a directed distance because there's some direction going on here. So if this value is positive, it means point P is to the right of the origin. And if this value is negative, it means that point P is to the left of the origin. So x is the horizontal distance, and y is the vertical distance. And again, it's a directed distance, meaning there's some direction to it. So if y is positive, it means we're above. If y is negative, it means we're below. So this is what we're used to for describing a point in the plane. It's called the Cartesian coordinate system. A lot of times we also call it rectangular coordinates, and you can kind of see why. So we have this rectangular or Cartesian coordinate system that we use. What we're going to be looking at today, though, is the polar coordinate system. And this is more involves circles. So circles are going to be in portions of circles, and rotating around the circle is going to be a lot of what we talk about. So first of all, what is the polar coordinate system? So again, we're going to have this origin, this one point that we pick, and this is where this kind of focuses our attention, and then we're going to describe all of the other points in the plane relative to this one location. So this is our origin here. A lot of times we just call it O. And then we're going to have an axis, but this is going to be our polar axis. And normally this corresponds to the positive x-axis. So we have our origin, and then this, think of it as like the positive x-axis here. But this is really our polar axis that we're going to do. And so if we had a point just sitting there on the plane, how we describe this point in polar coordinates is with r comma theta. So that first value, r, represents the distance. So r represents the distance our point is from the origin. It's the distance between these 2 points, r. Theta is the angle. So theta is this angle right here. So it's the angle starting at the polar axis, and it's how far we would have to rotate until we get to this line OP. So it's the angle in between our polar axis and this line right here. And these two coordinates, knowing the angle that we need to make with the polar axis and how far away we're from the origin, those two values are enough to fully describe every single point in the plane. And so this is going to be the setup for our polar coordinate system. All right. So just a few conventions before we get really started using these. So when we talk about the angle theta, we're usually talking in radians. And just to keep in mind, we're dealing with circles, so there are 2 pi radians in a complete circle. If theta is positive, well then we're going to go around the origin in a counterclockwise direction, and if theta is negative, we're going to go around the origin in a clockwise direction. And this is just a convention that we use. So, if theta is positive, we have our origin here, we have our polar axis, and we're going to go around in a counterclockwise direction. So something like that. That's how we're going to measure angle theta. Now, if theta is negative, we're going to go in the opposite direction. So again, we have our origin, we have our polar axis. All angle measurements start from the polar axis. But in this time, we're going to go clockwise around. So we're going to start at the polar axis, and we're going to go in this direction. All right, so that's some of our conventions for angles. Now for r, think of it like the radius. If the r value is 0, well then our point, no matter what theta is just going to be the origin. So again, think of r as the distance our point is away from the origin. So if the distance is 0, well, it means we're right at the origin. So no matter what theta is, if the r value is 0, then we're just describing the origin. So the origin actually has an infinite number of possible polar coordinate representations. And this is actually going to be true for all of the points in the plane. They're going to have an infinite number of possible representations. And we'll see this we'll talk more about this in a little bit. But specifically, if r is equal to 0, then we're at the origin. Now, what about here if we're dealing with a negative? We want to be able to allow negative r values in some cases. And so the way to think of this is if we negate the r value, what we're doing is we're really reflecting our point through the origin. So this gives us a way to think of having a negative r value in our point description. So let's consider the case. Draw a little example here where we have our origin, we have our polar axis, and then let's say that we had some other point here, and this was r comma theta. Well, if we were to negate that r value, it's going to be like doing a reflection through the origin. So should be a straight line connecting these points here. And what we're going to have is, if this is the point r comma theta, if we reflect this through the origin, we're going to be down here. Somewhere down here. Sorry about that. Let me clean this up. Can't really, running out of room. So if we have our polar axes and our origin, try to redraw this here. Here's our polar axis, here's our origin, and we have some point r comma theta. Let's look at the line connecting those points. So we have our origin, we have our point, and we wanted to investigate what happens when we negate the r value. Well, we're going to take this r comma theta point and just flip it, reflect it through the origin. So negative r comma theta would be just on the opposite side of the origin. So here's our origin, here's r comma theta. Negative r comma theta would just be on the opposite side. So this is going to give us a way to describe points with negative r values. And we'll see more about this in a little bit. Another way to think of this, though, is we're just taking this point r comma theta and we're just rotating it around the origin, halfway around the circle, essentially. So another way to think of negative r comma theta is we can think of this as r comma theta plus pi. So negative r comma theta is here. If we rotate this point halfway around the circle, so we have a radius of r. If we rotate this point halfway around the circle, we already started with an angle of theta. Halfway around the circle is going to be pi. So this point here, negative r comma theta, we could really think of it two ways. We could think of it with this negated r value, or we could have this plus pi in the angle, and it's doing the same thing essentially. All right. So let's get into what kind of graphing points in polar coordinates is going to look like. And it comes down to really knowing, or at least it helps to know some of the important angles. So here's the unit circle, and we're going to look at some of the important angles along this circle. And this is going to be helpful for not only identifying the angles, but also when we start looking at evaluating trig functions, this unit circle is going to be helpful to keep in mind. And in the first quadrant, so when we think of the usual, here's our origin, and then we have, the x and y axes, we can kind of break it up into 4 quadrants. So we have our first quadrant here. And then we're going to go counterclockwise around the origin. So we have our second quadrant, our third quadrant, and then our fourth quadrant. And there's important angles that occur in each of these quadrants, and we want to be able to know what they are or be able to figure them out. And so the most common ones occur in the first quadrant here. So theta equals 0 corresponds to this positive x-axis. And then we have pi over 6, we have pi over 4, pi over 3, and then here's pi over 2. And then this keeps going. And, essentially each quadrant has some of these important angles. So let's kind of go through and list what they are. And then we'll see how, if you don't necessarily have it memorized, how you can kind of figure out what the angle is each time that you're working with a polar coordinate. So the next one here is 2 pi over 3, then 3 pi over 4, then 5 pi over 6, and then we're at pi. And then we're at 7 pi over 6, 5 pi over 4, and then 4 pi over 3, and then 3 pi over 2, and then 5 pi over 3, 7 pi over 4, and then 11 pi over 6. So these are all of the important angles. And if we go around the circle, if we go around one full time, if we start at 0 and we go around the circle one full revolution, then we're back to 2 pi. And so 2 pi would also be, theta equal to 2 pi would also be describing the positive x-axis. Same thing with like 4 pi or negative 2 pi. All of these are going to be describing the positive x-axis. So it's just multiples of 2 pi here. We just go around the circle, in the case of 4 pi, we're just going around the circle for 2 times, and then we're back to where we started. All right, so these are all of the important angles that we're really going to be talking about over the next, few lessons. And how can we figure these out? So maybe, you need to have the ones memorized in the first quadrant, but once you have those done, you can kind of figure out the rest of them based on just rotating around the origin. So let's try pi over 4. So let's look at this pi over 4 wedge. Let's look at this wedge right here. And let's see how we can get the rest of the values by just taking this point and rotating it by copies of pi over 4. So if we rotate starting here, say this is our starting point. Let's rotate it pi over 4. That would take us right to here. Well, let's rotate another pi over 4. So we get another one of these pi over 4 wedges. So if we rotated this point another pi over 4, that would take us to here. 2 pi over 4. So this is 2 copies of pi over 4, also simplified to just pi over 2. Let's do it again. Starting here, let's do another pi over 4 rotation counterclockwise. So we get another wedge. Here's our other wedge. So this is another pi over 4 wedge. And now we've done 3 copies of a pi over 4 rotation. And that's what we have. 3 times pi over 4. So we've done 3 copies of a pi over 4 rotation to get to this point. So we started at 0. 1 took us to this pi over 4. 2 took us to pi over 2, or 2 pi over 4. 3 took us to 3 pi over 4. And then you could keep going and just work your way around the origin. So just work your way around the, think of it like a clock almost. So if we did 4 pi over 4 wedges, that would take us to pi. And if we did one more, let's say, here's our 5th pi over 4 wedge, and takes us to 5 pi over 4. So again, when we see this 5 pi over 4, it's helpful to think of it as 5 copies of pi over 4. So we did 1 copy, 2 copy, 3, 4, 5. And you can keep working your way around to figure out what the theta values are from there. All right. So, and we'll do this on some of the examples too. So you could do that for every single one of these angles, and to use this strategy to help fill in the rest of the chart here. All right, let's try an example. We're going to look at the point 2, 5 pi over 6. So this is, again, when we talk about a point that's given in polar coordinates, the r value comes first and the theta value comes second. And a lot of times we want to start with that theta value. So the first thing we want to do is we want to find, where does theta equal 5 pi over 6? Which ray directed out from the origin is this 5 pi over 6? And so when we write that down, theta is equal to 5 pi over 6. Again, it's helpful to think of that as 5 times pi over 6. So we start with our pi over 6 ray, which is right here, and imagine just rotating that 5 times. We're just going to rotate 5 times around the origin like that. So here's our pi over 6 wedge, and we're just going to do 5 of those. So here's the second one, here's the third one, the fourth one, and then the 5th one. And that means this is 5 pi over 6. So we have 5 of these pi over 6 wedges. This is the ray starting at the origin going out this way, ray corresponding to theta equals 5 pi over 6. Now we could have just had that memorized, but in case you forget, or in case you only want to memorize just the first quadrant, you can figure out where all the other ones are by just kind of counting up how many of those wedges you need. All right, so we're on this ray right here. So this gives us where to plot our points. And then we look at the R value. So the R value here is 2. So what we're going to do is we're going to start at the origin, and we're going to count out 2 units along this ray. So if we're starting at the origin, here's 1 unit and then 2 units. And so this is the point. This is 2, 5 pi over 6. That's our point there. So it's 2 units away from the origin, and it sits on that ray 5 pi over 6. And notice that it's on this circle that has a radius of 2. All right, let's try this other one. 3, 5 pi over 2. Again, positive R value. The theta value is 5 pi over 2. So we want to identify what ray is this. So let's think of this. Instead of 5 pi over 2, let's think of this as 5 times pi over 2. So where is the pi over 2 ray? Well, that's the positive y-axis here. So it's this whole big wedge. And we're going to do 5 copies of that. So here's our first big wedge. So that's 1 copy of pi over 2. Then here's our next big wedge. So here's our second copy of pi over 2. Then another big wedge. Our third copy. Another big wedge. This is our 4th copy of pi over 2. So far, if we've started on this ray here, this is theta equals 0. Then doing 1 copy takes us to pi over 2. Doing a second copy takes us to pi. Doing a third copy takes us to 3 pi over 2. Doing a 4th copy takes us back to our polar axis, but now we're at 2 pi, theta of 2 pi. And so we want to do 1 more copy, and that's going to take us right back up to here. So this is going to be another way to represent the positive y-axis, not only with pi over 2, but also with 5 pi over 2. So this is just another way to represent the positive y-axis. So when we draw this point out, we're going to be drawing it somewhere on this ray. And so this is where the R value comes in. So the R value here is 3. So we're going to count, starting at the origin, we're going to count 3 units onto that ray. So we're going to go 1 unit, 2 unit, and then here's our 3rd unit away from the origin. So that's our point. So what is it? 3, 5 pi over 2. So there's essentially what we did here is we went fully around the circle once, and then we went an additional pi over 2 units, or pi over 2 radians around the origin. So another way to think of this is we can think of this as 2 pi plus pi over 2. So this 2 pi here means we just went fully around the circle. So we started on the polar axis, we went 1 time around the origin, so we're back to where we started, and then we just kept going another pi over 2. So that gave us the ray 5 pi over 2, which really is describing the same section here as pi over 2. All right, let's try another example. Plotting some points on our polar grid. This time we're going to have a negative theta value. So here's a negative theta value. So we have the point 2 comma negative 3 pi over 4. So when we look at this theta value, again, it's helpful to really kind of at least think of this. You don't have to necessarily write it, but think of it as really negative 3 times pi over 4. So pi over 4 is kind of our standard rotation here. We're going to rotate 3 times, and we're going in the negative direction. So that means we're going to go clockwise. So the negative here is telling us the direction, 3 is telling us how many times, and pi over 4 is telling us how much. All right, so if we go back to our grid here, pi over 4 occurs halfway in between pi over 6 and pi over 3. So pi over 4 is halfway. So roughly like here, this is pi over 4. So a pi over 4 rotation in the positive direction, so if we were going to do a pi over 4 rotation in the positive direction, that would give us this wedge right here, starting at the polar axis going counterclockwise. We don't want to go in the positive direction, we want to go in the negative direction. So instead, we're going to start at the polar axis, but we're going to go clockwise. So that's going to give us this wedge right here. So this would be negative pi over 4. So we've done a pi over 4 rotation, but we've gone in the negative direction. So we just want to do that 2 more times. So we want 3 in total. We're going to do this 2 more times. So if we did it again, that would give us this wedge right here. So we have 2 of these wedges, of these pi over 4 wedges going clockwise. And that would take us to negative pi over 2. So we've seen that we can represent this negative y-axis with 3 pi over 2, but we can also use negative pi over 2. And then we just have to do, we want 3 wedges. Let's get another wedge here. So let's rotate another pi over 4 units clockwise. And we can see we're going to end up over here. So we've done 1 pi over 4 rotation starting at the polar axis, 1 pi over 4 rotation to get to negative pi over 4, 2 of those rotations to get to negative pi over 2, and then we do a third one, and that takes us to negative 3 pi over 4. So this gives us an idea of where we are on the plane relative to the origin. So we're going to fall onto this ray right here. And then once we've identified the location, then we figure out how many units we are going to be away from the origin. So we're going to be 2 units away from the origin. So if we start at the origin, we're going to count 2 units onto that ray. And so here we are. We're going to be on this circle of radius 2. So we're right here. And this is our point 2 comma negative 3 pi over 4. All right, let's try the other one. Now here we have a negative r value, so we're going to see how to handle that. All right, so first of all, we want to identify the angle 2 pi over 3. Where does that fall on our polar grid here? And again, it's helpful, not necessary, but helpful. Think of this as 2 pi over 3 rotations, or 2 pi over 3 wedges. So where does pi over 3 fall? Well, pi over 3 is going to be right here. And let's clean these out now. So a pi over 3 wedge or a pi over 3 rotation, is going to look like that. And we just want to do 2 of those. So here, if we start on our polar axis, if we do 1 of those rotations, it takes us up to this pi over 3 ray. And we just want to do it again. And so if we do it again, get another one of those wedges here, another one of those rotations, we're going to end up right here. So this is the 2 pi over 3 ray. And you might have it memorized, but in case you don't, if you have the ones in the first quadrant memorized, you can kind of figure out what all the other ones are. So this is the 2 pi over 3 ray. Now, our R value here is negative. So if it wasn't negative, what we would do is we'd just count 4 units out onto that ray. And that would give us, it's not the point that we're actually interested in, but this would give us 4 comma 2 pi over 3. So if we negate the R value, if we're going to look at negative 4, what we're going to do is we're still going to be looking at this ray 2 pi over 3. We're going to start at the origin here, but then we're going to go in the opposite direction. So we've identified this 2 pi over 3 ray. We're going to start at the origin, but then we're going to count 4, essentially 4. We're going to take 4 steps back. So we're going to take 1, 2, 3, 4. We're going to end up right here. And so this is the point negative 4 comma 2 pi over 3. All right. And there's really another way to represent this. So, there's other ways to represent this point. So if we wanted to, we could rewrite this without a negative R value by instead figuring out, well, what angle, what ray does this point fall on? So let's figure it out. What ray does this point fall on? Well, this is 2 pi over 3. If we do another one of those wedges, so that would take us to 3 pi over 3, which we usually write as just pi. Then if we do another one, here's 4 pi over 3. And then if we do one more wedge, that gets us to the one we're on, which we could also write as 5 pi over 3. So another way to write this point is with a positive R value, but then 5 pi over 3. So these two very different descriptions or representations are actually describing the exact same point. So, if we make that R value positive or negate whatever R value we have here, we just add pi essentially. So we're just going halfway around the circle. So starting at this point here, 4 comma 2 pi over 3, we're just going halfway around the circle. So we're adding pi. So we get 5 pi over 3 here for our angle. So there's different ways to represent these points. And that's going to be kind of a frustrating part of dealing with polar coordinates is if we have a point r comma theta, there's actually an infinite amount of possible representations for that point in the polar coordinate system. So we could describe it as r comma theta plus 2n pi. Or we could describe it with, if we negate the r value, then we just add on a copy of pi. So here n is any integer. And when we look at, say, this 2n pi, really what this represents n complete rotations around the origin. in whichever direction. So if n is negative, then we're going in the clockwise direction. If n is positive, then we're going in the counterclockwise direction. But n just describes how many times we're going around the circle, essentially. And you can see here we have the 2 and the pi. There's 2 pi radians in a full circle. So n is just the number of times we're going around the circle. So we can really represent this point r comma theta. We can just add or subtract as many copies of 2 pi as we want. And it changes the polar coordinate representation, but we're still at the same point. So we're just going around the circle and we end up back where we started, essentially. Now, if we negate the r value, if we look at this theta value here and do some of the multiplication here, so negative r theta plus 2n plus 1 pi. If we multiply this out, we have theta plus 2n pi plus pi. So really this 2n pi here is really just how many complete times are we going around the origin, and we get back to where we started. And if we negate the r value, then we have to add pi on. So we do 1/2 turn around. So this is like our half rotation, adjusting for the negated r value. So 2 pi rotation is a full, or a 2 pi is a full rotation around the circle. Pi, half of that, is just a half rotation. So if we negate the r value, then we have to adjust our angle by adding pi. So that's like a half rotation. So there's a whole bunch of possible ways to describe a point in polar coordinates. Usually we want to go with a more standardized approach. So for the most part, we want r to be positive and theta to be in between 0 and 2 pi. And if we put this extra restriction on it, then we're guaranteed to have, each point except the origin is only going to have one representation. So this kind of narrows our focus down. And so normally we try to go for a standard representation here, or a standardized format where r is positive and theta is between 0 and 2 pi. All right. So in example 3, let's say we're given the point in polar coordinates 2, 13 pi over 6. And what we want to do is we want to represent this point with another pair of polar coordinates with these conditions. R we want to be positive, and we want theta to be in between 0 and 2 pi. So r is already positive, so that's good. Let's look at this theta value. So let's look at, we have 13 pi over 6. And really what we want to identify, if the r value is good, it's positive, we just want to see how many extra copies of 2 pi do we have here. And so to deal with that, let's see if we can see how many copies of 2 pi we can break off. And so we can break this fraction apart. We can write it as 12 pi over 6 plus pi over 6. And we know that 12 divided by 6 is 2. So this is going to be 2 pi. So we're going to end up with 2 comma pi over 6 plus 2 pi. And so this 2 pi really isn't going to do anything for us. It's just we're going to go around the circle completely one time, and then we're going to go pi over 6 additional radians as we rotate. So like if we were going to draw this out, we have our origin, we have our polar axis, and usually it's helpful to just have kind of our normal pi over 2, pi, and 3 pi over 2, just to kind of fill this in a little bit. And we know pi over 6 falls right here. So essentially what this 13 pi over 6 is doing is it's essentially taking pi over 6 and adding 2 pi. So if we start at our polar axis here, we're going to go one time fully around the circle. So we basically get back to where we started, and then we go a little bit extra and then just finish it off by doing an additional pi over 6. So to really, there's some redundancy here. So to represent this point subject to these conditions, we can really just get rid of that 2 pi. And so another representation for this point is 2 comma pi over 6. So instead of going all the way around the circle and getting back to where we started, let's just cut that out and just do the pi over 6, the interesting part. So say our point here would be 2 comma pi over 6. So we find the pi over 6 ray, and then we count 2 units out from the origin. So this would be our point. Now let's see what would happen if we wanted to write that point with a negative r value, again with a theta value in between 0 and 2 pi. Normally we wouldn't want to do this, but we're kind of just practicing here. So let's see what this would look like for a negative r value. And so when we when we negate the r value, we have to adjust the theta value then. And the way we do that is by adding or subtracting pi. So if we negate the r value, then add pi to theta, or subtract pi from theta, however you need to in order to fit the inequality. So if we're at the point 2 pi over 6, what we're going to do is, to get this other representation, we're going to negate the r value, so we're going to get -2. And then we have to adjust the angle then. So instead of pi over 6, we're going to either add or subtract pi. If we subtracted pi, it would take us outside of this inequality, so we're going to add pi. So we'll have pi over 6 plus pi. And so what does that look like? What does this ray look like, pi over 6 plus pi? Well, here's pi over 6. If we do halfway around the circle, it means we'd be over here. So halfway around the circle, so this would be this would be 2 comma, what is this? 7 pi over 6. So this point over here would be 2 comma 7 pi over 6. We don't want this point. We want this point right here. So we have to, when we negate the r value, that's what sends us a reflection through the origin and sends us back to the point that we're interested in. So to kind of think of this, if we're starting with this point 2 pi over 6, the adding pi to theta takes us halfway around the circle, and then negating the r value sends us back through the origin. So, you know, we can come up with these different representation for points. And here we see that if we, whatever the r value is, if we negate it, so maybe you have a double negative here, this process would be the same. But in this case, we have a positive, we negate it, we get -2. And then to adjust for that, we also have to adjust for the angle. We add theta or subtract theta if needed. So again, we started at our point. The adding pi to theta takes us halfway around the circle, so it would take us here. We don't want to be here. We want to be right here. So negating the r value sends us on a reflection through the origin back out to this point. That's the point that we wanted. So another way to represent this point is with -2 comma 7 pi over 6. So that would be just getting a common denominator. So a lot of these points have many different possible representations. So you can play all sorts of games like this. All right, so next time we're going to see how to, we have these points that are being described in polar coordinates. Next time we'll see how to convert back and forth between a Cartesian coordinate system and a polar coordinate system. So we'll see you then. Bye-bye.